Epoxy resins are high-performance thermosetting resins that display a unique combination of properties. Epoxy resins have been commercially available for almost a half-century. Epoxy resins are arguably one of the most versatile polymers, with uses across an enormously wide variety of industries. The outstanding physical properties exhibited by epoxy resins include low cure shrinkage, no volatiles given off during cure, compatibility with a great number of materials, strength and durability, adhesion, corrosion and chemical resistance, and electrical insulation. Furthermore, epoxy resin systems are capable of curing at either ambient or elevated temperatures, and they require only minimal pressure during the cure. Thus, epoxies can be applied and cured under many adverse conditions, including outdoors. These properties provide great added value in many industries engaged in product assembly. Many new applications are being developed that will ensure the prominence of epoxy resins in the future. For example, epoxies are the material of choice for the reinforcement or consolidation of aging or damaged concrete structures, including walls, ceiling beams, bridge columns, and anchoring mechanisms. They are the main binders for graphite-reinforced composites, such as those used in manufacturing tennis rackets, fishing rods, skis, snowboards, and golf club shafts. They have also been used for manufacturing high-strength, lightweight carbon fiber pultrusion as replacements for steel rebar in special concrete expansion projects. Industries using epoxy adhesives include aerospace, civil engineering, automotive, chemical, electrical, marine, leisure, and many others. The prevailing reason for the broad acceptance of epoxy resins in these important and diverse markets is their capacity to provide a good balance of handling characteristics and ultimate physical properties. They adhere well to a very large variety of substrates, and they generate tough, environmentally resistant films or matrices. One of the major advantages of epoxy chemistry is the wide latitude it provides the formulator for solving technical problems. Epoxies can be designed to be flexible or rigid, high or low modulus, homogeneous, filled or foamed, conductive or insulative, fire retardant, and resistant to heat and chemicals. One of the chief advantages of epoxy resins is that they generally allow easy incorporation of additives, and the resulting formulation can be easily adapted to many manufacturing processes, such as pultrusion, lamination, filament winding, molding, casting and potting, coating, and adhesive bonding. Epoxy resins are commercially available as either liquids or solids. The liquids are available as solvent-free resins, ranging in viscosity from water-like liquids to crystalline solids, waterborne emulsions, and solvent-borne solutions. Generally, the higher the molecular weight of the epoxy resin molecule, the higher the viscosity or melting point. Types of epoxy resins. There are many different types of epoxies that are commercially available. Based on chemical structure and functionality, they can be divided into bisphenol A, bisphenol F, novolac, aliphatic, or cycloaliphatic, and epoxy functionalized silicones. Bisphenol A diglycetyl ether, DGEBA, is a liquid epoxy resin produced from bisphenol A that is the most common and widely used component in epoxy resin systems. It is a thermosetting resin that forms durable, rigid, and heat and chemical-resistant materials after being cured with various agents like amines or polyamides. DGBO is a key ingredient in products such as adhesives, paints, coatings, and composites used in various industries. DGEBA is typically made by reacting bisphenol A with epichlorohydrin. It is a colorless, viscous liquid that can have a pale yellow or straw color in its commercial form. Bisphenol F epoxy, is structurally related to bisphenol A, BPA, a popular precursor for forming plastics, as both belong to the category of molecules known as bisphenols, which feature two phenol groups connected via a linking group in BPF. The two aromatic rings are linked by a methylene connecting group. In response to concerns about the health effects of BPA, BPF is increasingly used as a substitute for BPA. Novolac epoxy is a specialized type of epoxy resin that is derived from phenolic Novolac resins, which are modified with epoxide groups. This gives Novolac epoxy superior chemical resistance, high thermal stability, and enhanced durability compared to standard epoxies, making it ideal for demanding industrial applications. It is used in high-performance coatings, adhesives, and composites, where protection against aggressive chemicals and high temperatures is crucial. Aliphatic and cycloaliphatic epoxies are types of epoxy resins with unique properties like UV resistance, low viscosity, and excellent electrical insulation, making them ideal for outdoor, electrical, and high-clarity applications. They differ from traditional aromatic epoxies, such as those based on bisphenol A, because they lack aromatic rings, which prevents yellowing and provides superior weatherability. Cycloaliphatic epoxies contain one or more aliphatic rings, are produced by reacting cyclic alkenes with peracids, and are known for their high oxirane content and absence of chlorine. Aliphatic epoxies are a broader category that includes cycloaliphatic epoxies, as well as other types like hydrogenated bisphenol A and glycidyl ethers, and are often used as reactive diluents for viscosity reduction. Epoxy functionalized silicones are silicones modified with epoxy groups, which act as a bridge to incorporate the desirable properties of silicones into organic polymer systems. They are used as reactive intermediates and additives to improve properties like flexibility, high-temperature resistance, and water repellency in coatings and adhesives, and they can be cured via epoxy-compatible mechanisms. These compounds come in various forms, including those with pendant, terminal, or cycloaliphatic epoxy groups. Epoxy resins are composed of polymeric molecules that are converted to a solid by a chemical reaction. Epoxy systems physically comprise two essential components, a resin and a curative. The curative causes the chemical reaction, which turns the epoxy resin into a solid, cross-linked network of molecules. This polymer is called a thermoset polymer because, when cured, it is irreversibly rigid and relatively unaffected by heat. By contrast, thermoplastic polymers are not cross-linked and can be made to flow with the application of heat. Cure of the epoxy resins is initiated once the resin is mixed with a curative. The cure of all epoxy resins is an exothermic process where heat is generated as a natural result of the chemical reaction. Success in using most epoxies is dependent on handling the product in the correct way to avoid premature cure and unwanted side reactions. Epoxy resins are not the lowest-cost resins potentially available for most applications. Thus, epoxy resins must provide added value to justify their additional cost. This added value is usually realized by the incorporation of a special property or combination of properties into the final product.